Well, hello everybody. So, in the last class we had started the distillation, the process of distillation, and I had given you a brief introduction about the different distillation processes, and we had mentioned that we will be discussing first the flash distillation, then the rectification or the fractionator, and then the batch distillation column. So, today we are going to start our discussions, or rather I will be giving you a brief overview of the design considerations for designing a flash distillation column. Now, as we had already mentioned, or as it was discussed in the last class, what do we have? We have a feed. The feed composition is F, and the the feed flow rate is F, and the composition is denoted by HFI, and the feed, it is usually heated in a preheater. This preheater, it heats the feed such that after it is throttled through the valve, it reaches the condition where it can flash to form the vapor and the liquid streams which meet the composition specifications which are specified. The compositions can be specified either with respect to the vapor product or with respect to the liquid product. So, therefore, the feed preheater, it is required in order to ensure that vapor liquid flashing occurs in the flash drum. The equipment used for flash distillation, it is usually called the flash drum, and so therefore, just to ensure the preheater is used. Instead of the preheater, we can also supply heat inside the flash drum by either inserting coils here or maybe by a jacket. And usually for such cases, condensing steam or a condensing fluid is used to provide the heat. But in such cases we find, we do it for very small units, but for such cases we find that since the heat transfer coefficient, it is controlled by the liquid inside the drum. So, therefore, it is less, and therefore, the heat transfer is not so efficient. So, usually we prefer the preheater. From the preheater, then it goes to a restriction orifice. This restriction orifice, it simply flashes the liquid such that the two phase mixture forms here. So, it is needless to say that the restriction orifice is placed as close to the drum as possible, such that the entire flashing occurs inside the drum and the vapor liquid separation can happen here. Once it happens, as I have told you, the vapor rises. The vapor flow rate, as I have already mentioned, it is V, and usually these are multi-component mixtures, usually they are used, and so therefore, the composition of each component is denoted by Yi, and the liquid it is drawn, it is L, and the composition is given by Xi. Now, after separation, it always happens that the liquid which forms small droplets. So, therefore, these droplets, they can be drawn out with the vapor just in order to arrest the liquid droplets and to ensure that almost dry vapor ensures from the flash drum. We have demister pads which arrest the liquid and prevent the liquid passage along with the vapor. These flash drums, they can be vertical or they can be horizontal as well. In a horizontal flash drum, we find that the demister pad is usually located near the vapor outlet line. And the choice between the horizontal and a vertical flash drum, that depends on certain considerations which will be discussed in details when we will be discussing the pressure vessels. For the moment, it is sufficient for you to remember that usually for vertical flash drums, the length to diameter ratio is around 3 to 5. When it exceeds 5, generally we go for a horizontal flash drum, And in a horizontal flash drum, what happens? Naturally the vapor, it has to flow through a larger path. So, therefore, we get a greater distance for vapor liquid separation, and while it is flowing, the vapor velocity decreases, and so therefore, the separation is naturally better. And based on this, and so definitely when the head space is limitation, we go for a horizontal. When the float space is limited, we go for a vertical. So, with all these considerations, we select whether we will take a vertical or a horizontal vessel. Now, whatever we take, it is quite evident what are the things that we need to control in a flash drum. The first thing is the pressure. How is the pressure controlled? The pressure is controlled, as you can see, the control valve is there in the vapor outlet line. So, by regulating the vapor flow, the pressure inside the drum is controlled. The other thing that we need to control is the liquid level here. So, for controlling the liquid level, there is a level controller which is again regulated by regulating the flow rate of the liquid outlet. These are the two basic things which need to be controlled, right. And the condition is such, as I have already mentioned, the condition in the flash drum should be such that on flashing, the vapor and liquid stream that we get, they meet the specifications. The specifications can be specified either in terms of the yield. Maybe this is the amount of vapor fraction we require, or in terms of product purity. Say for example, for the more volatile component, we need this much amount of product separation. It can be anything of that sort, right. So, therefore, now if we have to design this particular flash drum, tell me what are the inputs that we already know. Definitely we know the feed flow rate F, we know the composition ZFI. Again, you just recollect, it is ZFI because it can be XFI or it can be YFI. So, we definitely know this. After the preheater, we know the temperature of the feed, we know the pressure of the feed. So, the feed enters here, right. Now, once the feed enters here, then it flashes, and as I have told you that the pressure inside the drum, it is regulated by a control valve which is placed in the vapor line. So, therefore, by means of the control valve, we can control the pressure inside the flash drum. So, once we know the pressure inside the flash drum, say for that particular P flash, we have the TXY plot here, right. So, therefore, now how do we proceed with the distillation of the design of the flash drum? So, suppose we know the composition, right. Now, once it is flashed, definitely it will lie on this particular line. During flashing or when it is flashed, since it is separating into a vapor and a liquid feed, so quite naturally it should lie on this particular vertical line between the dew point curve, or it should be between the dew point and the bubble point. So, therefore, the flashing should be such that the temperature, it lies between the temperature of the flash, this should lie between the dew point of the feed and between the bubble point of the feed, right. So, therefore, accordingly, since P flash can be regulated, accordingly we can select a T flash such that the T flash lies between the bubble point and the dew point, say at somewhere at this particular instant. So, at this particular point, we can definitely find out, corresponding to T flash, we can find out the saturated vapor pressure for each component I. How do we do it? If you recollect, during my discussions on equilibrium, we had told you that P saturated, it is obtained from Antoine's equation. What is Antoine's equation? P saturated for any component I, it is equal to AI. AI means the Antoine constant corresponding to component I minus Bi plus T flash plus log 10 P saturated I. This is equal to T flash plus Ci. So, for each component Antoine constants are available. So, accordingly from there we can find out, once we know T flash, we can find out P saturated I for each of them. Once we can find out P saturated I for each of them, then from there what we can do, we can find out Ki. If suppose we are dealing with hydrocarbon distillation, that case usually we are dealing with the adjacent members of the homologous series. For such cases we can assume that the system is an ideal system. For an ideal system, you already know Raoult's law, it gives you YIP equals to XIPI saturated, as a result of which Ki, it is nothing but equal to Pi saturated by P. If it is a this is for an ideal system. If it is for a non-ideal system, then quite naturally this here we are going to have a gamma, and accordingly Ki, it is going to be gamma I Pi saturated by P, right. This is there for a non-ideal system. If a system is non-ideal, then in that case, along with Antoine equation to find out Pi saturated, we also need some particular activity coefficient model in order to find out the gamma I. And as I had already mentioned, the activity coefficient models which are usually used, they are either the NRTL model or the Uniacke or the Wilson model, something of that sort. So, now once Ki it has been found out, then suppose, see, just from the just I will write down the basic mass and component balance equations. What is it? We know F equals to L plus V, this is V, this is L and this is F. We also know for each component we can write it down as Lxi plus Vyi. Now, from these two equations we can find out Xi for each corresponding thing. We substitute Yi as Ki Xi, and we can also substitute L as F minus V, and then from there what we can do is, and then from there we can find out each particular Xi in terms of F, and we can denote the V by F as a ratio, and therefore, from these two equations we can find out Xi as Zfi by 1 minus V by F into Ki minus 1. Instead of V by F, you can also write it down in terms of L by F. In that case, you have to just substitute this with F minus L. So, therefore, for each composition if we write down, and we know that sigma Xi has to be equal to 1, which automatically implies that this has to be equal to 1. So, therefore, if we can write down this equation for each case, then from this particular equation we know everything except V by F. So, therefore, we can, from this equation we can find out V by F, and once we can find out V by F, then for each particular V by F we can find out Xi, just the way I had written. For each particular V by F, Xi, it corresponds to, it can be obtained from this equation. Once we can find out Xi, we can find out Yi as Ki Xi, right. Now, once this whole thing has done, then after that we need to see whether the pressure that we had assumed, for which this was the Txy diagram that we have gone. See, the pressure and the temperature conditions, they can be adjusted, just keeping in mind that both have to lie between the dew point and the bubble point, right. So, therefore, what we can just do an enthalpy matching in order to find out whether we have reached the correct value of V by F and whether this is fine. How can we do it? We can definitely find out the vapor enthalpy HV, we can do it. We can find out this HV is nothing but sigma Ni HVI for each and every component. We can find out the outlet enthalpy along with the liquid. This will be HL, which is sigma NiL, this should be NiV HLi. So, therefore, we can find it out. We know what is the feed, what is the enthalpy which is entering from the feed. The feed was throttled. When it was throttled, then therefore, the enthalpy just after the preheater we know, the same enthalpy is there once it is throttled. So, therefore, we are in a position to find out HF. Now, under assuming that there are no heat losses etc. So, therefore, under balanced conditions what do we expect? We expect that the enthalpy in should be equal to the enthalpy out. So, what do we do for this particular case? Suppose we define the enthalpy difference as your HV plus HL minus HF, and we find out what is this delta H. Quite naturally, if suppose this delta H, suppose it is positive, then in that case what do we have to do? We have to reduce the flash temperature, and then we have to repeat the calculations which I have mentioned, right, starting from the from assuming the T flash and finding out Pi saturated. From there we have to start and we have to continue this, right. So, therefore, this is the way by which we can find out, we know F, we know HF. The things which are required to find out is we will be finding out V, we will be finding out Y, we will be finding out L, we will be finding out Xi, and if we assume that we know P flash, then in that case we will be finding out T flash by this particular process. Well, so therefore, from the inputs that I have mentioned, what are the deliverables? The deliverables definitely they are going to be the operating temperature and the operating pressure of the flash drum, which I have already discussed, flow rate and composition of the vapor and the liquid streams, that means Vy and Lx, which I have discussed, feed preheat temperature and the preheating load if the preheating is required, and accordingly if the jacket details or the heating coil details if suppose the drum is heated. And finally, after we do all these things, the next thing that we need to finalize is the drum dimensions and also the internal fittings like the demister pads, the vortex breakers and the nozzle connections and the locations. There is, before I go to discuss the drum dimensions, there is one more thing. We suppose by some means we would, this I will discuss. If suppose there are conditions where we need to operate the flash drum under vacuum, when do we need it? It is quite evident that under conditions, if you observe this part where I have got a graph, if I can show you the graph, I think I do not have it, anyhow I had already discussed it, that when we go for lower and lower pressures, quite naturally the difference between the bubble point and the dew point, it increases, and so naturally we will be getting a much better separation. So, therefore, it can happen that under conditions where you need to recover a large amount of the lighter component as per your specifications, you might have to operate under vacuum. Under that conditions, you have to find out the vacuum requirements. But I will be discussing shortly that what should be the optimum pressure, how we should be selecting the optimum pressure and temperature. One thing I just wanted to mention, just like I had told you about a demister pad, in the same way we also need a vortex breaker. What does the vortex breaker do in this particular case? In this particular case, here the liquid is there. As the liquid goes out, it can take up some amount of vapor along with it. So, the vortex breaker, it breaks the vortex such that disengagement between liquid and vapor happens. But this has got a much more important purpose. See, after this, what happens? The liquid, definitely it will be going to some particular storage or something. So, therefore, the liquid, it will be pumped out from here and it will be taken. Now, you very well know that if a liquid vapor mixture is introduced in a liquid pump, just recollect the phenomena of cavitation which happens. So, therefore, you can understand the greater requirement of a vortex breaker in this particular case. Well, after the vapor flow rate etc. has been decided, then the drum has to be sized. Now, usually the sizing, it is based on the total mass flow rate of the vapor, which you can find out once you know V in moles per hour, you know the molecular weight, you know the composition, you can find the mass. So, based on the total mass flow rate and the maximum allowable vapor velocity on the liquid surface, you can find out the drum diameter, right. Now, the maximum allowable vapor velocity, this can be found out from a system factor, and the liquid and the vapor velocities. The system factors are given as a function of the separation factor in this particular table for a horizontal drum and for a vertical drum. And we find that if the system factor is higher, then it allows a higher UV max. If it allows a higher UV max, a lower cross section of the drum can be obtained. So, therefore, an alternate way of finding out the diameter can be based on the disengagement height also. Okay. When we have a higher disengagement height, naturally what it does, it reduces entrainment. When it reduces entrainment, we can operate with a higher SF, and so therefore, the second approach is to find out SF based on the disengagement height. So, whatever be the technique you use, you can find out SF values. Once you can find out SF values, you can find out UV max. Once you have found out UV max, you know the mass flow rate. So, therefore, based on them, you can find out the diameter of the flash drum. Normally, this diameter, when we will be discussing the pressure vessels, you will find that just to confirm 2 coats. So, therefore, it is usually rounded off to confirm 2 coats, and those things we will be discussing later. Just very briefly, the whole thing will be much more clear when you do a problem. I will just mention the design considerations which you should keep in mind when you are discussing or rather when you are firming up the design. First thing is, definitely, as I was telling you, we would prefer a lower operating pressure. When you go for a lower operating pressure, it is quite evident that the temperature requirement for line between the bubble point and the dew point, that is definitely lower, quite evident from here. When that is lower, definitely the heating load will be lower. But at the same time, you have to remember that if you have to go to pressures much lower compared to the atmospheric pressure, then in that case what happens? There will be every chance of some leakage of air into the column. Suppose you are dealing with a hydrocarbon column, then in that case what happens? That due to this leakage, there is every chance that an explosive mixture will form. So, therefore, we have to keep that into mind also. And again, if you are going for operating in a vacuum, I have already told you the problems. So, keeping everything in mind, we would like to operate under a condition where it is going to be operationally safe, it is going to be feasible, and most importantly, it is not going to be exorbitant. The next thing is, which I have already mentioned, that whether we should have a heating arrangement integral or whether we should have a preheat. The other thing is the yield. Now, in order to optimize the yield, it is very important for us to find out the combination of the flash pressure and the yield, such that we can get the maximum yield of the desired stream. Choice between horizontal and vertical drums I have already mentioned, and the demister pad, it is a very standard bought out item, I have nothing to say on it. The whole thing will be little more clear when we discuss a problem on flash distillation.
Dear students, you already have been given an introduction to the flash distillation, and here I am to give you an example of a design procedure for designing a flash distillation column. Well, you can call it a column, you can call it a drum, but normally it is called a drum, a flash drum. The problem at hand is that of a contaminated stream of orthoxylene which is available from a plant, and it is contaminated by benzene. The content of benzene is 10 mole % in the stream, and the flow rate of the stream is roughly 2 kilomole per second. This contaminated stream can be used again if the benzene content can be brought below about 6 mole %. We are supposed to design a flash distillation system for this purpose. To start with, what we do is we make a summary of the problem. So far what we know is the flow rate is simply 2 kilomole per second, that is the feed rate. So, F is equal to 2, ZF, the mole fraction of benzene, the lighter component in this system is 10%, the mole percentage is 10%. So, XF equals 1, and the maximum benzene content at the bottom is 6% mole. So, naturally we decide for the moment that XB is equal to 0.06. We also know that if we can achieve something slightly lower than that, it will give us a margin, maybe 5.9 or something. Now, what we do is we go for the process scheme, we have a look at it. You can see here that the feed comes through some sort of heating arrangement, a preheater. Then what you have is a restriction orifice here which is close to the drum. So, basically upstream what you have is a higher pressure and a higher temperature, and downstream of the orifice is having the pressure of the drum itself, where the pressure is something like P flash and the temperature is T flash. So, naturally the phase separation occurs at a temperature of T flash and P flash, which we do not know yet. So far what we know are only two parameters, my feed rate is 2 kilomole per second and my ZF is 0.1. The liquid maximum composition here is 6%, which is 0.06 XB. We do not know any other parameter at the moment, but tentatively what we decide is we are going to go for a drum, and we do not know yet and we have not confirmed, but tentatively we may have a demonstration pad there or we may not have it also. Now, at this point what I would like to point out is it is absolutely important before any design to decide on the battery limit. That means, what is the connections to the external world of the section that you are going to design. So, I am going to draw it here and define my battery limit as this. Naturally, the liquid goes out as well and the vapor goes out as shown here. So, we are supposed to have the conditions at this point, and at this point. And the process conditions within will be the temperature of flash and the pressure of flash. So, once we have decided this, what we do is we go for data collection. The system contains benzene and orthoxylene. The molecular weights are given here, the normal boiling point in Kelvin is given here as well. The density approximately of the liquid density, we do not consider that it is varying too much with temperature and pressure right now, and we put these as the expected density of 0.8787 and 0.8800 grams per cc, which amounts to 878.7 and 880 kg per meter cube. In order to calculate the vapor pressure, we are going to use the Antoine equation here. The The Antoine equation is applicable typically when as long as your prediction remains below 2 atmospheres. And here it is a low pressure system, it is pretty I will say a volatile system, and in this specific system Antoine equation is applicable, that we know from the thermodynamic fundamentals. We are not going to go into the details of that. The specific heat of the liquid phase at an average value kilojoule per kilomole Kelvin, the values are 134.8 and 187, and the heat of vaporization at normal boiling point is also noted as 30.77 and 36.24 kilojoule per kilomole. We are going to use all of this data as we proceed. Now we go for the process design procedure. The first thing that we need to decide is on the drum pressure. This is a hydrocarbon system which is inflammable in mix with air. So, we will prefer that the drum operates at a pressure above the ambient pressure. That means, it operates at a slightly above atmospheric pressure of around 1.1 atmosphere absolute, which is 1.1 into 101.325 kilopascals absolute here. This would prevent ingress of air in the form and forming explosive mixture. So, according to this, we decide the P flash is going to be this much value, that means 1.1 into 101.325 kilopascals. The next step is to estimate the bubble point and the dew point temperatures for the feed. Why we do it? Because we know that the feed will vaporize fully at dew point, and it will be 100% liquid at its bubble point. So, obviously, my flash temperature T flash is bound to be something between these two temperature values. So, we move forward to the estimation of dew point and the bubble point. The basic equation, the first is the equation number 1, which is nothing but the Antoine equation, which is written here for the ith component in general. The constants are given there. In fact, the same equation is also there in that particular table of data. We have already understood and we know that Ki, the distribution coefficient, is given by gamma I into Pi saturated upon P, P being the total pressure of flash. And this being a simple system, gamma I is going to be nearly 1. So, henceforth we are not going to use gamma I, because we are going to consider it to be 1. The third equation, which is equation 3, is basically a summation equal to 0. It basically is a simplified form of sigma xi minus sigma yi equals 0. So, what we have here right now is a set of 3 equations, which will definitely have to be satisfied for the case of equilibrium. Let us move forward beyond this. The first thing that we calculate is the dew point, for which my V by F equals 1. So, what we do is we assume a dew temperature. Correspondingly, we know the vapor pressures, so we can very easily evaluate the Ki values. Then what we do is, since we already know the Ki values and V by F is equal to 1, we evaluate the left hand side of the equation 3, that means the summation expression, and check if it is close to 0. If it is not, we have to reassume T dew till we come to a convergence. At the point of convergence, of course, within a tolerance, you will possibly while working will never be able to get it 0, but it is also possible for you to find the value of T dew in a way. If you plot your left hand side of the equation value here, and if you plot it like this, you will definitely find corresponding to a particular value of 0 in my left hand side expression, there will be a particular value of, there will be a value of T dew, and this is what is your solution. In this specific case, what we did is exactly the same, and we note that my dew point is 145 degrees centigrade, which is 144.9 as per calculations. And this is for the feed which has got xf is equal to 1, and this dew point is corresponding to a P flash of 1.1 atmospheres. Exactly in the same way we solve for the bubble point, for which we know that my V by F is going to be 0. We evaluate Ky, we evaluate the left hand side, and we find that the bubble point is 134.5. The next is deciding the flash temperature, which has to lie between these two, 134.5 and 144.9. Quite naturally, we assume a T flash value which is lying between these two, evaluate Pi values, evaluate the Ki values, and we also assume a trial value V by F, and evaluate the left hand side, and if we check if the summation is 0 again. If it is not, we have to try another value of V by F till we get the convergence of that summation value or the left hand side value coming close to 0. At this particular point, what we don't know is that we have arrived at the V by F value for a corresponding T flash. For example, after this, what we are going to do is we are going to calculate the value of the liquid phase composition for each component, which is xi, which is given by this expression. Since we know the Ki values, since we know the V by F values, and the Ki values are corresponding to a temperature of T flash, for every T flash there will be a particular V by F for which the convergence happens, and there is a corresponding x. We find here in my first trial the values are 137.5, 0.09 and 0.08. Beyond that, what we have is a case which we find is quite satisfactory, in the sense here we have a temperature, flash drum temperature of 140 degrees centigrade, and my bottom temperature, bottom liquid has got 5.9% of benzene, which is 0.059 is the value of x. And so, this is an acceptable solution with a very small margin, of course, in my composition. What we do now is definitely based on this, we put down all the values here. We know the feed, we naturally know the compositions as well. So, we note down, and we note that the flow rate of the vapor and the liquid values are here. The composition of the vapor and the composition of the liquid, they are also known here. And the operating conditions here are 140 degrees centigrade and 101.5 kilopascals, which is absolute. The next question comes that in order to achieve this, we got to have upstream of the orifice, that means downstream of the preheater, a particular amount of enthalpy. And this enthalpy will be the sum of the enthalpy of the vapor and the liquid stream which are leaving. So, what we do is we find out, since we know the temperature and pressure of the vapor and the liquid streams, we use these two equations to evaluate the liquid and the vapor enthalpy at 140 degrees centigrade, and we find these values to be 24355 for HV, and for HL it is 25689. The total basically is the sum multiplied by the individual mass flow rates. So, natural mass molar flow rates. So, this gives us the rate at which the enthalpy leaves this particular system. In other words, we also know this amount of energy has to enter the system as well. Enthalpy has to enter the system by preheating. So, what is next? We find the preheat, we know the value of enthalpy, we know the CPL values, we know the feed composition. So, naturally the T preheat can be found out by evaluating this expression. H is known, CPLI values are known, ZFLI values are known, and I ask you individually to do this part and evaluate the value of preheat. Now, it is also essential that it should not vaporize at this particular location. So, the pressure here has to be above the bubble pressure of the feed at this preheat temperature. So, naturally the next thing is basically the minimum pressure to avoid vaporization is estimated as the bubble pressure of the feed at T preheat. The next part of it is finding the size of the flash drum. Here basically the sizing is done, the diameter is found out, or the cross section of the drum is found out by finding out the maximum allowable vapor velocity at the vapor liquid interface, which is given by this particular expression, which involves rho L, rho V and a factor SF. There is, in order to find out SF, we require one more parameter, which is small s. The value of SF at 85% flooding velocity, the separation factor SF, is found in the table which I am going to show you next. This corresponds to a particular value of S. So, this is the table. In fact, what we do is we look at this value, we look at this value, and we will find that our value of S lies in between these two, and we will be making a linear interpolation in this. So, what we do here is we simply evaluate, and we find my S value is 0.4318, the interpolated SF naturally from the table is 0.085, and there is a correction to UV based on this, which slightly reduces it to 0.0844. We know the mass flow rate, mv for the vapor, rho v is my vapor density, and UV max, which we have just found out to be 0.0844. So, by putting these values, we find that we require an area cross section of the vapor liquid interface to be 0.442 meter square. If you have a circular vertical drum of diameter d, quite naturally the minimum diameter turns out to be 0.75 meters. So, what we do is we have found out the dimensions, and we make a design summary. There is something which is still left out. We have not found out the height. The basis of height I am just telling you here, but it will be dealt in more details when we discuss about the design of such drums, which are vapor liquid separators, which this one is practically so. And this height consideration is basically, if you have a liquid level here in this particular drum, from which liquid is going out, and here basically the level should be such that in case you have any interruption in L, the level rise should be such within that time you can correct the interruption, so that between this level and this level, if it rises within this or it falls within this, in that case we should be in a position to take the corrective action on the L. That means, this basically is decided on the rate of flow of L, and you require a sufficient time to ensure that a corrective action on L can be taken in case of emergency, and that would allow a variation of L, but within a limited range. You already have decided the diameter of the vessel, which is minimum 0.75, possibly you will be going for 800 millimeter diameter, and you know the value of L in meter cube per hour. So, you decide the residence time accordingly, and you finally decide that this is going to be your basic design, which consists of a design summary of the process scheme and the instrumentation, summary of all process data and physical dimensions. Thank you.